Hello everyone, my name is Dal Ibrahim and in this video I'll be sharing my approach to modeling the Zhuhai Jinwan Civic Art Center using Grasshopper for Rhino. The project is located in Zhuhai, China and is designed by Hadid architects. It brings together four major cultural venues beneath a continuous flowing roof structure which is inspired by waves and flight. The building sits at the edge of the water, reinforcing its relationship with the surrounding landscape. The overall geometry is composed of four petal-like forms, two of which are mirrored across a central axis. While the layout is symmetrical left to right, each petal varies in shape and depth. A central courtyard and roof opening creates a visual and spatial anchor, allowing light in and guiding movement between the venues. In elevation, the canopy reveals its angled surfaces and interlocking roof geometry. The roof is covered with a paneling system that follows the curvature of each petal and reinforces the directional flow towards the center of the composition. Branching columns rise from intersections within this grid, visually connecting the canopy to the ground in a dynamic way. At ground level, the project features stepped platforms, bridges, and water-adjacent walkways that define access points and circulation while integrating the building into its coastal context. I began constructing my base geometry by starting with a three-sided polygon, which I rotated twice to form the star-like figure that represents the outline of my building. I then exploded those polygons in order to extract the points and draw guiding lines from the center of the shape to each point in order to generate the form. And then from those points, I created those two surfaces representing the petals found in my canopy. And although my building is symmetrical right to left, the individual petals differ in shape and depth. And to reflect this variation, I scaled the two base surfaces independently, resulting in the first and second petal geometries. And the scale of this petal can be manipulated using this number slider. Moving on to the canopy subdivisions, I used two different approaches, one for each petal. For petal number 1, which had fewer subdivisions, I used the graph mapper to generate the panels, and then I wanted to remove the corner surface, so I deconstructed the B-reps and then reconstructed the surface, blending the edges together to create this clean unified geometry. And then to shape the canopy, I used a kangaroo solver. I placed a sphere within the petal, scaled it, and then projected target points onto the sphere to serve as anchor points. I also used the move in the Z component to exaggerate height variations in selected points, and this was the final result of the first solver. For petal number 2, I used Weaver Bird Sierpinski carpet and mesh window components to generate more subdivisions, and this is the result. For kangaroo, I used a similar logic, but was a bit more dramatic because some panels needed to be rotated. I again used a sphere, scaled it and rotated it to project anchor points. And for the curved side panels, I used arcs as target anchors instead of spheres, and I also applied loads to enhance the deformation. This is the result of the second solver. Finally, for the double-layered wing beneath the edge of the second petal, I used the third kangaroo solver, and I applied a z-axis movement within an expression x minus 20 to reduce the height by 20 units compared to the main wing, achieving the secondary wing, and this is the result of the last solver. For the paneling, I diagonalized each mesh, then used the stripper to deconstruct it, culled the edges and rebuilt the surfaces. I applied Weaver Bird's mesh window to create the panel openings and then added thickness. And each panel was processed individually since applying the pattern to grouped panels caused issues with the geometry. Now that I have all the panels, I extracted their edges and lofted between them to generate the connector surfaces, which act as transitional panels between the petals. And once the connector surfaces were created, I moved on to refining the mesh geometry. I used the Weaver Bird's picture frame and Catmull-Clark subdivision to smooth and enhance the mesh. And then I applied thickness to the frame in order to give the canopy its structural depth. For the columns, I used the intersection points between the petals, moved them downward, and extracted the connected roof edges. By evaluating the curves, I created adjustable points that keep the columns attached to the canopy. The entire setup is parametric, allowing for easy control over the column height and position. I used multi-pipe to generate the columns, however they were cylindrical, which is not similar to reality. So I applied the Catmull-Clark subdivision to give them a more realistic rectangular form. And for the building, I started by taking the result from the kangaroo solver and extracting the edges. I then used evaluate curve to create adjustable points that follow the outline of the plan. These points were projected to the ground, and then I extruded them vertically to generate the building mass. And to define the glass facade, I applied a quad panel followed by a Weaverbird's mesh window and a picture frame to create the glass panels and mullions. For the ground, I started by constructing the outline from the base geometry and added the bridges at the top and bottom. I then took the 4 corner points on the right and left edges and moved them downward to create a sloped surface that connects to the water. The stairs consist of one main V-shaped stairs and 2 tiny ones on the edges. The V-shaped stairs were created by offsetting the building outward, then scaling the curve to get the top and bottom outlines. I used the tween curve component to generate a series of steps and lofted them to form the stair surface. And for the guardrails, I created rectangles of varying sizes to reflect the way the railing grows taller and then gradually disappears. I then lofted the sections and used the flow component to wrap them along the edge of the bridge, giving them a continuous dynamic form. This is the overall form of the building.